Okay, so let me to contribute to the conference with the following lecture. We will talk about a joint paper with Mohamed Amouche and Pilar Romero, when we try to explore the hypercyclicity of the element in the lambda commutant of the Hardy-Bauer shift. Okay, so the notion of hypercyclicity is quite simple. About the linear operator on a separable infinite dimensional Hilbert space is said to be hypercyclic if there exists one vector x such that the orbit is dense. And we say that the operator is supercyclic if, of course, the operator is not hypercyclic, but there exists one vector x such that the project with orbit is dense. That is the orbit with the help of scalar multiplets. Okay. The motivation of this result are the following results by Godefroy and Shapiro and Vladimir Müller. They are interested in to extend hypercyclicity phenomena to the whole commutant of a given operator. For instance, Godefroy and Shapiro proved that if capital L is an operator that commutes with the differentiation operator on the space of entire function, then the operator is hypercyclic provided it is not a multiplier of the identity. Let me to say that this result is a little surprising because you consider this question on the Banach space setting in presence of a uniform norm, the contractions are never hypercyclic. So when there is a norm on the underlying space, we can obtain similar result. But we can obtain similar result for supercyclic operator. Specifically, Vladimir Müller solving a long-standing question posed by Godefroy and Shapiro proved that if an operator commute with a generalized backward shift B, and this operator A again is not a multiplier of the identity, then the operator is supercyclic. Let us recall that an operator B is a generalized backward shift if the kernel of B is one-dimensional and the linear span of the kernels of the powers of B is a total set. Okay, the linear span is dense, right? So given a complex number lambda, we say that a bundle linear operator X is said to be a lambda extended eigenoperator of T if we have the following commutativity relation. Tx is equal to lambda xt. And the general question here is to know how hypercyclicity and supercyclicity are transferred to a bigger set, which is the lambda commutant of an operator, right? And in this sense, we have obtained some result. For instance, we prove that L is a continuous lambda eigenoperator of the differentiation operator, then L is hypercyclic if and only if the modulus of lambda is bigger or equal to 1, and L is not a multiply of a composition operator induced by anything endomorphism of the plane, of the complex plane. And for supercyclicity, we get that an extended lambda eigenoperator L is supercyclic if and only if the modulus of lambda is between 0 and 1. L is not a multiply of a composition operator induced by anything endomorphism. and the following unexpected condition. The phi must be 0 on the origin, okay? So let us start with our result, but keep in mind the following sufficient condition for hypercyclicity. It is an spectral sufficient condition discovered by Godefroy and Shapiro. Roughly speaking, say that if the point spectrum is big, then the operator should be supercyclic. Specifically, if the linear span of the kernel corresponding to eigenvalues of modulus less than 1, and the linear span of the eigenvector corresponding to eigenvalues bigger strictly than 1, if both sets are dense, then the operator is hypercyclic. Now let us remember a classical theorem by Shields and Valen of the 70s that characterize when an operator commute with multiplication by sec, which is the forward shift. One operator commute with the forward shift if and only if the operator is a multiplier, a Hardy multiplier. That is an analytic Toeplitz operator induced by a bounded analytic function. Therefore, one operator commute with the Hardy backward shift if and only if the operator is the adjoint of a analytic Toeplitz operator, right? And with this characterization of the commutant of the Hardy backward shift, and also with the spectral condition discovered by Godefroy and Shapiro, they was able to characterize when an operator that commute with the backward shift is hypercyclic. They proved that an operator that commute with the Hardy backward shift is hypercyclic if and only if the image of the unit disk on their phi intersect the unit circle. And the question is, it is immediate. Let us suppose that T is an operator that lambda commute with the Hardy backward shift. Is it T hypercyclic or when T is hypercyclic? And assume that T is an operator that lambda commute with this time with a generalized backward shift. Is T supercyclic? Okay. First of all, we need an extra result by Petrovic. Okay. Petrovic characterized the operator that lambda commute with the Hardy backward shift. Okay. Specifically, Petrovic showed that there exists an extended lambda eigenoperator of the backward shift if and only if lambda is in the closed unit disk. And the following result complement Petrovic's result. If the modulus of lambda is 1, then an extended eigenoperator factorized has R lambda, which R lambda is the dilation operator, by phi acting on B, when phi is a bounded analytic function. The operator phi of B is just the adjoint of the multiplication operator induced by phi, right? However, when the modulus of lambda is strictly less than 1, then the extended eigenoperator factorized has a dilation operator by the adjoint of a multiplication operator. At this time, the multiplication function is an element of the Hardy space. This class is actually a Hilbertian operator space, and we don't know more about this operator space. We don't know anything about its structure, right? Okay, Now, let us suppose that the modulus of lambda is less than 1. Okay, by previous result, we get that the standard lambda eigenoperator is never hypercyclic. So we concentrate with the modulus of lambda is equal to 1, okay? And we obtain, the first result is that the spectral condition by Godefroy and Shapiro for the inducing operator phi of B is a necessary condition, okay? If the eigenoperator is R lambda phi of B, modulus of lambda is equal to 1, then the operator T is hypercyclic, then the spectrum of phi of B must intersect the unit circle. That is, the spectral condition is necessary for hypercyclicity of the standard lambda eigenoperator. However, the condition is not sufficient. We consider here lambda, the imaginary unit, and we consider these two maps, phi0 and phi1. So the inducing operators, analytic Toepley operator, they are joined. The spectrum is big. However, this operator to the power 4 must be also hypercyclic, but it's not. Okay, we see here the following examples. The spectrum of the inducing maps is big. However, in one case, T0 to the power 4, the point spectrum intersect the unit circle. So this operator is hypercyclic by a deep resolved by Shamin Ansari. And on the second one is not hypercyclic because it does not intersect the unit circle. Okay. So as a consequence, the same ideas can be used to characterize hypercyclicity of a standard lambda eigenoperator when lambda is a root of the unity. If lambda is a root of the unity, then we can characterize the hypercyclicity of the standard eigenoperator just by considering the adjoint of the multiplication operator phi of z, which is the product of the following n functions. Okay. However, when lambda is an irrational rotation, still is an open question. We obtained some results which depend on the dynamics of the product of this function. Okay. For instance, if we consider the product of these n functions, we can obtain sufficient condition for not hypercyclicity. Okay. More specifically, if we consider these two product of functions, infinite products, then we can get positive result in terms of the dynamic of the function phi n and omega n. Okay. For instance, we can obtain results of the following, like this, right? And for hypercyclicity, we can get that if we consider a generalized backward shift and an element in the lambda commutant, we can obtain a result, a Godefroy and Shapiro type results for the lambda commutants. Specifically, if B is a generalized backward shift on a Banach space X and A is an standard lambda eigenoperator of B, if the kernel of A contains the kernel of B, then the operator A is hypercyclic. However, Vladimir Mueller result is not longer true for the lambda commutant of the backward shift. We get it that if the modulus of lambda is less than 1, and R lambda phi of B is an extended lambda eigenoperator such that the inducing map don't vanish on the origin, then we have an element in the lambda commutant of the backward shift which is not supercyclic. Okay. So the concluding remarks of our result is that hypercyclicity is not transferred as well to the lambda commutant in presence of a uniform norm in the space. If we analyze Godefroy and Shapiro result, we see a dichotomy. If the adjoint of the multiplication operator is not hypercyclic, then the powers of the multiplication operator of its inverse are power banded, that is, are quite regular. And we think that a dichotomy theorem is waiting to be proved that establishes that the element of the lambda commutant of the backward shift are either hypercyclic or they have orbits which are quite regular. Okay. Finally, let me to say that this result was published this year in Journal of Mathematical Science. And thank you very much for your attention.